Hit record. All right. All right. Hi, everybody. Thanks for coming to another EERI seminar. Today we've got Dr. Joseph Gomez, excuse me. He's a research civil engineer at the Engineering Research and Development Center Dash Construction Engineering Research Laboratory, which is one of the laboratories that is in the research arm of the U.S. Army Corps of Engineers. His research interests include a lot of experimental geotechnics, in situ testing and instrumentation, scale modeling of geotech structures, slope stability and soil stabilization. And because his lab is so multidisciplinary, he also has interests in geotechnical engineering with synthetic biology, chemistry, and material science to help solve problems that normally elude geotechnical engineering. He also got his bachelor's, master's, and PhD all at the University of Illinois in Urbana-Champaign. So with that, please take it away.
Many thanks for the introduction, Noah. All right, let me just move this over here. All right, so good afternoon. Now, before I start, I'd like to acknowledge Professor Patron. Thank you so much for giving me the opportunity to present to your students. So I apologize for not being there in person. I originally planned on it, but things are, we'll say, a little bit weird right now as a federal employee. Otherwise, I would have been out there presenting to you all in person. So speaking of being a federal employee, I'd like to quickly highlight my institution. I'm coming at you from the Construction Engineering Research Lab. We like our acronyms here in the government, or in the military rather. So that's CERL. Now, CERL is one of the 7 labs in the Engineer Research and Development Center, or ERDIC, which is, like Noah mentioned, the research arm of the U.S. Army Corps of Engineers. So there are other labs that comprise ERDIC, and these are the Cold Regions Research and Engineering Lab, or CREL, the Geospatial Research Lab, GRL, the Coastal and Hydraulics Lab, CHL, Information Technology Lab, ITL, the Environmental Lab, EL, and the Geotechnical and Structures Lab, or GSL. The majority of our labs are located in Vicksburg, Mississippi, with the exception of CREL, CERL, and GRL. So CREL's in Hanover, New Hampshire, GRL in Alexandria, Virginia, and CERL in Champaign, Illinois. CERL it's co-located, with the University of Illinois campus, and I say co-located because although we are on U of I land, we're actually like 5-ish miles off campus. Apparently, that's because when the building was being constructed, it was during the Vietnam War, and the U of I was worried about, fire bombings and such, just the normal construction stuff. But as you can tell by the name of each app, we all have kind of a certain focus. CERL's name, it doesn't suggest much, so its mission happens to be quite broad. Indeed, we have quite a smattering of academic disciplines here. And like was mentioned in my intro, many of my projects, for example, involve synthetic biology, chemistry, and even there's some archaeology and historic preservation in there. We were doing some work on adobe houses together. Finally, I'd like to acknowledge the contributions that my colleagues at the University of Illinois have put into the work as well. So now that you know a little bit about me, let's jump right into it. So the topic of this presentation is on the development of correlations for the cone penetration test that practitioners can use for, say, a first pass analysis or something like that. So what we're going to do in this presentation, we're going to smash together a few seemingly unrelated concepts, talk about the method in which I fuse them together, and also discuss some of their utility. Right. So, and let me know if you're not seeing that. So why should you be interested in this? Well, I mean, I feel like this comes down to engineering research in general, right? This research, these correlations, they can save you time and money. So let's explore this, right? So the cone penetration test, or the CPT, is a repeatable, reliable, and cost-effective tool for site characterization. It provides a constant log of cone tip resistance, sleeve friction, and pore pressure, among a number of other important measurements which can be correlated to important engineering properties. But even considering these advantages, the CPT is often accompanied by other in situ and lab tests. So while these accompanying tests complement the CPT and clarify the interpretation of its data, they can also be time consuming. So in consideration of this, the correlations presented herein are intended to be used solely with the CPT without any additional in situ testing or lab testing, without iteration or numerical modeling. In other words, like I said, these correlations can save you some time and money. And also, considering that this is an EERI meeting, these correlations have applicability to liquefaction susceptibility, although that framework is admittedly, it's still in the works. All right, so let's check out what our agenda is for this presentation. We're going to cover our material in 4 sections. So in section 1, I'm going to introduce some of the foundational concepts that will come up again and again. Specifically, I'm going to introduce the cone penetrometer and the calibration chamber. I'm also going to discuss the delta Q soil behavior index, as well as the critical state line, or the CSL. So then I'll wrap up the introduction with just a quick overview of the CPT database that we use to develop all of the correlations. In section 2, we're going to discuss the compressibility concept, which it describes how I aggregated the calibration chamber data for interpretation. Section 3, we're going to talk about the methodology that I use to develop these correlations and how these correlations relate delta Q to things like the y-axis intercept of the critical state line, the slope of the critical state line, the state parameter, as well as relative density. And finally, in section 4, we're going to go over the development of a delta Q-based correlation to forecast cone tip resistance. We're going to relate that then to an overburden normalization. All right, so let's move on to this background. Okay, so the cone penetrometer. Now, the CPT can generally be described as an instrumented soil probe composed of a cone mounted at the end of a series of rods that are pushed into the ground. So the CPT obtains readings from its different sets of instrumentation, as well as it is advanced into the ground. The CPT typically measures friction resistance, rather resistance caused by penetration at the cone tip and along the friction sleeve. So the measured cone tip resistance is referred to as QC, while the friction sleeve resistance is referred to as FS. Now, while we're on the topic of cone tip resistance, I should mention that there are more variations than you can shake a stick at, but I'll introduce these as they come up. In addition to these measurements, CPTs also contain several other types of instrumentation, and one type I'd like to mention is the piezometer, which measures pore pressure. So piezometers they could be mounted at different locations on the cone, which are noted here in the diagram as the U1, the U2, and the U3 location, with U2 being the most common. All right, calibration chamber testing. So the data that I use to interpret the correlations presented herein are from calibration chamber tests. So what is a calibration chamber? Well, from the schematic, you might be able to see that the calibration chamber, it's kind of like a huge triaxial chamber. You can apply vertical stresses and generally lateral stress, and in some cases you can apply water pressure or pore pressure as well. So they are used to rigorously study the performance of CPTs as well as other in situ tests under laboratory controlled conditions where soil properties, stresses, and strains can be accurately measured. All right, the delta Q soil behavior index. This really is a huge part of my work. So in 2017, Say et al. Introduced the delta Q soil classification and behavior index. Delta Q describes a linear relationship between effective stress normalized cone tip resistance, or capital QT. And I make the differentiation there because there's also a lowercase qt. So you'll hear me call it out. and effective stress normalized friction sleeve resistance. Now that we're on the subject, let's take a minute here to discuss the various types of cone tip resistance. So in addition to capital QT, there's little qt, which is the total corrected cone tip resistance. This particular cone tip resistance accounts for the effect of pore pressure, which is essentially to say that water pressure acts on certain parts of the cone and causes the readings to drift. In sands, you know, QT is essentially equal to QC. So in this presentation, you're going to hear me refer to both interchangeably. So let's see. We also have QT, little qt net, which is a variation of the cone tip resistance that accounts for the effects of overburden pressures. So getting back to delta Q. So delta Q is actually the slope of a line created when capital QT is plotted against Fs over sigma prime V. And it's given by the equation shown here. So delta Q applies to soils ranging from sands to clays to peats, though like all behavior indices, it has limited applicability to structured and sensitive soils. Furthermore, I should clarify, or I should note that delta Q is relatively unaffected by overconsolidation. So this is a big, this is one of the big benefits of the delta Q soil behavior index. And I should also point out that the delta Q, it has an offset origin kind of over here, over at Fs over sigma prime V equal to negative 0.067 and capital QT equal to negative 10. All right, so really quick, the critical state line. Critical state it's the state at which soil continues to shear with no increase or decrease in stress or void ratio, which is to say the dilation rate is 0. So critical state is developed by plotting data obtained from specialized triaxial tests in void ratio effective mean stress space. The critical state line, or the CSL, is the locus of all the points obtained at the end of testing. So that is to say, after performing a set of tests, the data is plotted and the CSL would be interpreted through the endpoints of the data. The linear approximation of the CSL is defined by the equation that I'm showing here on the right. Let's talk about this equation really quick. So altitude, or capital gamma, is the x-axis, I'm sorry, the y-axis intercept of the CSL at 1 kPa. For the example shown here, the y-axis intercept at 1 kPa is 1.237. And compressibility, or lambda 10 in this case, meaning that the data was plotted in log base 10, is the slope of the CSL. Now, I should note that while the slope of this line is negative, the geotechnical convention is to report the compressibility as a positive number. So as you can see, the compressibility of the soil in this example is 0.145. Importantly, I should note that compressibility is the basis of the work that I'm presenting to you today. So let's move on to the state parameter, which is the equation here on the left. So the state parameter is the mathematical difference between the void ratio and the void ratio at critical state. So you can see two examples here, one with a positive and one with a negative void ratio. And the reason that's important is because the state parameter characterizes the density of the soil as a function of mean effective stress, where positive values denote contractive behavior in response to shearing and negative values denote dilative behavior. Just a few notes on soil compressibility, especially since it is key to this presentation. So the usage of the term compressibility in reference to penetration resistance can be seen in literature as early as the 1970s. And though the term had been in use for several decades, compressibility was at first just an ambiguous term that has become synonymous with the slope of the critical state line, starting with Bean et al. 1987. Recently, further work has continued to support that compressibility is correlated to cone tip resistance and friction sleeve resistance. But interestingly, compressibility is not directly accounted for in most soil behavior type systems. All right, so just a few words about this CPT database that I use. So CPT database is a relational database composed of the soil table, the chamber table, and the CPT table. And let's dive into those. So the soil table is composed of 24 sandy soils aggregated from 33 studies. The table represents soils having a wide range of attributes, whether that's altitudes, and you can see the ranges here, compressibilities, mean particle diameters, as well as maximum and minimum void ratios. So the chamber table represents 17 calibration chambers from 17 different studies. Now, I should mention that some chambers were used in more than one study, but this table too has a wide variety of parameters since it has, for example, a mini chamber that was made from a modified triaxial apparatus, all the way up to chambers that are, 1.5 meters tall and 1.6 meters wide. Finally, the CPT table. The CPT table contains 847 CPTs aggregated from 27 different studies. These tests represent also a wide range of parameters, whether that's vertical effective stress, horizontal effective stress, coefficients of lateral earth pressure, as well as overconsolidation ratios. I should mention that only about 100 tests had corresponding cone traces, and for these tests, I did compare the traces to the listed results to ensure, to the maximum extent possible, that the data was good. Otherwise, I used the values of cone tip resistance and friction sleeve resistance directly from the source. All right, let's take a look at this agenda again. So to recap, we've talked about the CPT, which is a soil probe. We've talked about calibration chamber testing, in which we can rigorously test field equipment like the CPT. We talked about the delta Q soil index, soil behavior index, and the CSL with special emphasis on altitude, or the intercept at hold on, the y-axis intercept at 1 kPa, the compressibility, or the slope of the critical state line, and the state parameter. With the background out of the way, let's move on to this compressibility concept, which was key to the interpretation of these correlations. So in this section, I'm going to tell you about how the compressibility concept can be used to group and interpret seemingly dissimilar data. So let's get right into it. Actually, I said let's get right into it, but let's talk about the state parameter concept. So before we get to the compressibility concept, let's start with this. The state parameter concept was introduced by Bean and Jeffries in 1985. So in their work, Bean and Jeffries performed triaxial tests on a number of soils, and then they plotted the results against state parameter to demonstrate the state parameter concept. Specifically, they tried to show that soils with similar values of state parameter will have equally similar behavior. So let's take a look at these plots so you can see what I'm talking about. So in this first graph, Bean and Jeffries plotted drain peak friction angle against state parameter. Examining the plot shows an apparent linear trend. And indeed, Bean and Jeffries interpreted a line through the data, which is this solid line here. That is to say, Bean and Jeffries were suggesting that soils with similar values of state parameter have equally similar values of drain friction angle. Now, I should note as well that they interpreted another line for this soil right here, Hilton Mines Tailing, which you can see in the dashed line. The reason they did this is because the trend for Hilton Mines did not fit with the other data, and I'm going to touch on that very shortly. So moving on, the volumetric strain at peak stress plot is similar in that there is an apparent trend. That is to say, soils with similar values of state parameter will have equally similar values of volumetric strain at peak stress. Once again, though, the Hilton Mines tailings did not follow their interpretation. So finally, Bean and Jeffries plotted dilation rate versus state parameter. And again, there is an apparent trend, which is to say soils, you're gonna hear me say this phrase a lot, soils with similar values of state parameter will have equally similar values of dilation rate. And once again, Bean and Jeffries made a separate interpretation for Hilton's Mines tailing. So that is to say that this is all to say that these soils should have similar behavior according to the state parameter concept. With this in mind, though, so Bean and Jeffries went on to suggest that the state parameter concept could be extended to more complicated situations, such as cone penetration. So before we look at the state parameter concept applied to the CPT, let's go back and look at this plot in its entirety. And I assert that the reason that Hilton Mines tailings did not fit with the other trend is because it has the compressibility it's about 3 to 7 times larger than the other soils. So now let me tie this to other work by Bean et al., in which they suggested that attempts to produce a unified framework for the CPT must include, and I'm paraphrasing a little bit here, the slope of the critical state line. All right, so let's go back to the CPT then. So here, Bean et al. Plotted cone tip resistance in the form of capital QT mean, which is the net cone tip resistance normalized by effective stress against state parameter. So here you can see that tests with similar values of state parameter had equally similar behavior. I'm sorry. I want to emphasize here, though, that this is just one soil. But what if we extended this to many soils with similar compressibilities? Well, that is the essence of the compressibility concept. So that is to say that the compressibility concept hypothesizes that soil behavior will be similar in sandy soils that have similar values of state parameter and compressibility. So with this in mind, let's look at the data in the database that we just talked about through the same lens that Bean et al. Did. That is to say, let's look at plots of capital QT mean versus state parameter. All right. So as you can see from the data, I've binned all the soils by compressibility and plotted QT mean versus state parameter. Then using a multiple nonlinear regression, I fit a curve to each bin to show that the data aligned in a predictable manner. Now, before we take a closer look at the data, I want to present the bins. So the data was binned over a range of compressibility of 0.04, starting from 0, which is not very compressible, to 0.56, which is very compressible. Now, I should point out that there are no data in bins 8 through 13. So let's take a closer look at this data. All right. So again, I've plotted QT mean versus state parameter. And the different soils are presented by different markers. While the trend lines, which were obtained again by multiple nonlinear regression, are shown in magenta. Now you'll notice there is a bit of scatter. This is an inherent part of calibration chamber testing and something that is addressed in more detail in the works that you can see here in the corner. In any case, you can see that the data tend to follow the regression. So again, I assert that soils with similar values of compressibility and state parameter will have equally similar behavior. Again, you're gonna hear me say that a lot. So let's explore this a little more and examine some even more compressible soils. So these are the least compressible soils, and we're moving into ones that are a little bit more compressible. So as you can see from this second set, the data continues to follow the regression. Even Hilton Mines tailings, which are these right-facing orange triangles. So I should note there is no data in the bins between E and F. And let's move on to this next set here. And as you can see in the final set, the data, even as it gets more compressible, continues to follow the regression. So I think this is a pretty clear indication that soils with similar compressibility and similar state parameters will behave equally similar. All right. So back to our agenda here. So now that I've introduced you to the compressibility concept, let's talk about how I used it to develop the delta Q-based correlations, which were then subsequently used to develop the delta Q-based overburden normalization. Okay, so specifically what we're going to talk about here is correlations relating delta Q to altitude and compressibility, which will allow the practitioner to develop a critical state line based on CPT data, as well as correlations for density, in particular state parameter and relative density. Okay, so I'm going to briefly introduce a couple of CPT-based correlations because we're going to revisit them shortly. That is to say, I'm going to present the performance of the delta Q-based correlations against these similar correlations. So first we have the SBT, or soil behavior type systems. Since our conventional CPT does not retrieve samples from which the soil can be characterized, researchers have developed these CPT-based systems, as well as individual correlations that go along with them that correlate to behavior and soil properties. So two popular systems are those proposed by Bean and Jeffries and Robertson and Ride. So these SBT systems use cone tip resistance and friction sleeve resistance to calculate an SBT index, which I've noted here as ICVJ and ICRW. Both systems have robust frameworks that are correlated to many important soil parameters. And unfortunately, time prohibits a detailed discussion on these SBT systems. With regard to altitude correlations, we found none in the literature. And as for compressibility, the Bean and Jeffries SBT index is correlated to compressibility, as is another correlation by Plews et al. As far as state parameter goes, both SBT systems have associated state parameter correlations. Um, Finally, there are also a number of relative density correlations in the literature, though, of course, we can't go into depth, unfortunately, on them here. So again, I mention all of these correlations because we're going to revisit them when we validate the performance of the delta Q based correlations. So here we're going to link the delta Q. We're going to link delta Q and compressibility. So indeed, a number of researchers out there have suggested that compressibility has a major effect on cone tip resistance and friction sleeve resistance. So relatedly, Bean, Jeffries, Robertson, and others have linked their SBT indices to compressibility. So considering this, I plotted compressibility and altitude against delta Q to examine their relationship. And let's take a closer look here. So I should note that only 6 sands were used for the compressibility and altitude correlations, and it's because they were the only sands in the database that had friction sleeve data. And I should note that the database I collected here is actually the largest database that exists in literature right now. So so although there's only 6 soils, that's the most that's out there. So between these 6 soils, though, there are 559 tests associated with them. Now, I want to note 2 issues with this smaller data set. One is the abnormally high value of delta Q for Hoxton sand and the abnormally low value for Ottawa sand. And you can see them to the left and right here. Now, the study for Hoxton sand dates all the way back to the early 1980s, so it is difficult to determine the cause of the issue, though. I suspect, however, that friction sleeve measurements were erroneously low. Indeed, a number of researchers, for example, Lune et al. 1986, Gillespie 1990, Robertson 1990, Lune and Anderson 2007, and Robertson 2009 have noted that friction sleeve measurements are less accurate and less reliable than cone tip resistance measurements. For Ottawa sand, the issue appears to be that the cone tip resistance is erroneously low. Recent work by Chen et al. 2022 suggests that cone tip resistance measured by miniature cones, which was used in the Ottawa sand study, may be lower than what is measured by a standard sized cone. Now, as far as the mathematical model goes, I selected an exponential formulation to model this data since more compressible sandy soils, which have higher values of compressibility, are unlikely to exhibit a value of delta Q less than 15 to 20. Additionally, the higher values of delta Q, at higher values of delta Q, values of compressibility less than 0.02 have not been measured. So let's see, I selected the same exponential formulation for the altitude correlation. Additionally, I selected the minimum value for the altitude as 0.07. The minimum for both the compressibility and altitude correlations were based on data from the database presented in GAMES 2024, as well as other databases from Stark and Olson, 2003, Jeffries and Beans, 2016, and Macedo and Vergere, 2022. So these databases contained critical state parameters for over 171 sandy soils and mine tailings, all of which fall in the ranges suggested by the correlations. All right, so the development of the density correlation. So I want to mention a few things that Robertson and Campanella noted on the correlation of cone tip resistance to density. So first, they suggested that there is a correlation between cone tip resistance, friction sleeve resistance, density, and stress history. They went on to suggest, however, that these parameters could only be correlated if one knows what the friction sleeve resistance should be for a normally consolidated soil at a given state, which is very, very difficult to do. You'll notice then that Robertson and Campanella suggested that friction sleeve resistance was highly correlated to density. And I want you to keep this in the back of your mind. So furthermore, they suggested that forecasting density using the CPT is unreliable because of variations in soil compressibility. And I also want you to keep this in the back of your mind. With that, having said that, I suggest that the delta Q interpretation addresses these concerns by removing the effects of stress history. So like I mentioned before, it's relatively immune to the effects of overconsolidation. So removing the effects of stress history to determine the variations in soil compressibility, using the compressibility concept to aid the interpretation by aggregating enough data to make rational interpretations, and by inverting the problem suggested by Robertson and Campanella. That is to say, given a certain compressibility and cone tip resistance, I interpreted normally consolidated values of density for a given cone tip resistance. So I should note that while Robertson and Campanella suggested friction sleeve resistance as being closely correlated to cone tip resistance, friction sleeve resistance, density, and stress history, Lamprix and Leonard suggested that actually cone tip resistance was closely related to sand type and state, a suggestion which I found to be the case. All right, so indeed, my interpretation of the data supported that cone tip resistance is closely related to state, although I found capital QT rather than QC to be a better fit. Like I mentioned, I interpreted normally consolidated values of density at a given cone tip resistance, and I did this by binning the data. So I should note that I don't show the charts here since they are quite large, and we of course are limited on time. And while I don't present these tables, I would like to note that note a couple important aspects of it, of my bins. So first is that the bins range in QT from a QT of 1 to just under 3,000. I should remind you that QT is dimensionless, so there are no units. From the range of 1 to 80, I used bins of 2, and I did this because it represents the range where soils would be the loosest. That is to say, there's a lot of curvature in the correlation in this range, and using smaller bins provided the finest level of detail. For capital QT over 80, I use a bin size of 20. And finally, I should mention that all of this was constructed using normally consolidated data. So let's take a look at the bin containing normally consolidated tests where capital QT is between 80 and 100, and for the state parameter interpretation. So like I mentioned, I bin the data, interpreted a normally consolidated trend through each bin. So what exactly are we looking at? All right. So what this plot is saying is that a less compressible soil needs to be looser to achieve a capital QT of 90, which is the average QT in this bin, while a more compressible soil would have to be denser to achieve that same QT. Now, I should mention that this bin is fairly representative of the majority of the other bins. There are 62 of them, though, so I cannot, of course, present all of those. It would probably bore everybody out of their minds. Hmm. All right, so for the relative density correlation, quite similar to the state parameter correlation. Notably, however, the direction of the trend is reversed. So again, as you can see, um, a less compressible soil needs to be looser to achieve a capital QT of 90 in this case, while a more compressible soil needs to be denser. As with the state parameter correlation, I've just shown one bin here that is representative of the other 60-something bins. All right, so the results of these interpretations leave us with correlations that are quite simple. First, the user just selects which parameter they're interested in, whether that's state parameter or density. And once that correlation is selected, the user would just then compute the coefficients, either A, B, C, or D, and then plug them into the equation. Now, I want to emphasize that these correlations can be computed directly from the CPT with no extra steps, no iteration, no numerical modeling, and no extra lab testing. And in consideration of the other SBT systems out there, these are actually very, very similar, very, very simple compared to those other ones. All right, so now that we've discussed all the delta Q correlations, let's look over their performance. So for the compressibility correlation, I want to emphasize again that there are a limited number of calibration chamber studies out there that have all the necessary parameters. Indeed, if it was out there, I put it in here. So the comparison of compressibility correlations is kind of limited in size and uses just the data from the database. I should note, though, that both Bean and Jeffries and Plews used a very similar data set to what I used. In fact, my data set builds off of theirs. So let's look over the results here. I've plotted the forecasted versus measured compressibilities for the three correlations I mentioned. And as you can see, the delta Q correlation, I mean, of course it does, because I modeled it off of the data. It performs well compared to the other correlations. You can see, though, that there are those two sands that are a little off. Those are Ottawa and Hoxton sands. And while time constraints preclude an extensive discussion on the data from these sands, let me just remind you that, again, I think it's the friction sleeve resistance and the cone tip resistance for each of these data sets that makes it a little bit off. I do, however, explain these issues in the references you see here at the bottom. In any case, the soils they all lay close to the one-to-one line. It is apparent, though, that each correlation has some difficulty in forecasting. But on balance, the delta Q correlation performs just as well as the other correlations. Now, finally, I want to mention that I go into extreme detail in these references to provide quantitative measures of performance for each of these correlations, which support my qualitative assertions here. So I'm not just saying it performed good. There are numbers to back it up. So to compare the state parameter correlations, I again plotted forecasted versus measured for the Jeffrey and Bean, Robertson, and the delta Q correlation. So let's take a closer look at these. All right. So as far as the state parameter correlations go, the Jeffries and Bean correlation, it tended to forecast a little bit denser than measured, though the effect is less pronounced when the state parameter is less than minus 0.20. Conversely, the Robertson correlation tended to forecast looser than measured with much of the data above the one-to-one line, whereas the delta Q correlation tended to forecast approximately equal both above and below the one-to-one line. So to compare the relative density correlation, I used a data set from Chapman that I did not include in my database since it didn't have all the necessary parameters needed to include it. I did not include the data here, of course, because of time, and the table is quite large. However, if you'd like to see it, just take a peek in these references down there. There are a couple things I do want to highlight, though. So Chapman performed 31 tests, 18 were normally consolidated, 13 over-consolidated. And you should note that the correlation, the delta Q correlation, was developed with normally consolidated data, but I present all the data. All right. So just a little bit about the test sand. The test sand, Frankston Cranbourne sand, it is a fine to medium, rounded to subangular quartz sand, average grain size, coefficient of uniformity, and coefficient of curvature, which you can all see here. Okay, so I did compare the delta Q-based correlation against a number of other correlations from literature, Main et al., Robertson and Cabal, and Olaya and Bray. And before we actually look at the performance of all of these correlations, it is important to note that Chapman discussed the difficulties of accurately measuring the relative density and suggested these values could be off by up to 20%. Experimental geotechnics is indeed hard, and that's where this uncertainty comes from. So with that in mind, let's take a look at this data. So to compare the correlations, I once again forecasted, I did forecasted versus measured. And in addition to the one-to-one line, I added that plus and minus 20% line to account for error that Chapman noted. Okay, let's look at this a little bit more closely. So between Main 2014 and Main et al., they forecasted much looser than measure. The forecasts, importantly, though, are all parallel to the one-to-one line. The Robertson, Cabal, Olaya, and Bray, and the delta Q correlations forecasted within plus or minus 20% generally of the measured values. Robertson and Cabal forecasted the closest, but it is interesting to note that the latest version of their CPT manual, so this is from the 2015 CPT manual, the update, however, does not include this equation, and I'm not sure why. In any case, the Olaya and Bray correlations forecasted the normally consolidated and over-consolidated data reasonably well, with the data clustered around the one-to-one line and mostly within plus or minus 20% of the measured values. The delta Q-based correlation tended to forecast the normally consolidated looser than measured, but again, mostly within that plus or minus 20%. While the over-consolidated data was clustered around the one-to-one line. So ultimately, it is difficult to determine which correlation is actually the most accurate. And again, that is the difficulty of experimental geotechnics. And one of the reasons I love geotechnical engineering so much, because it relies heavily on interpretation. And I think that's very interesting. Between all this stuff and the Main and Main et al. Correlations, I actually think that the sand is possibly a little looser than what they had measured. All right, so let's go back to our agenda. We've got the delta Q correlations in the rear view mirror. So we're going to move on to the section on the development of the overburden normalization. And what's funny about all this is I actually started with the normalization. While doing it, though, I realized that I needed a better way to interpret the data. That is to say, it was difficult to interpret the tests because they were from these like seemingly disparate data sets, and I didn't know how to fuse it all together and make the interpretation. So that's where the compressibility concept came in. So while I was doing that, though, I realized I didn't have all the soil parameters that I needed. So I made some tools to get it done. And that's where the delta Q correlations came from. So, all right, on to the last section. Now, before we talk about the delta Q-based overburden normalization, we have to go over a couple of, we have to go over the delta Q-based correlation to forecast cone tip resistance, as well as a little bit of background. All right, so this work, the delta Q correlation work is It's to forecast the cone tip resistance. It's actually based on work by Harmon and Baldi et al. And you can see that their work is a function of both relative density and effective overburden stress. What we did over here, though, was simplify the equation, though. So what we did is we held relative density constant, we changed QC to QT net, and we made all the terms dimensionless, and it gave us this equation. So this equation allows us to forecast dimensionless net cone tip resistance at a given relative density as a function of overburden stress. Now, using this equation, I did the following, but let me emphasize that this is difficult to visualize, so we'll discuss it here and just move right along. So first, I bin the data for each soil by relative density or by state parameter. Now, once again, I haven't included the table because it is quite large. You can, however, find it in these references here. So after binning the data, I fit the curves using the equation I presented earlier. Into the relative density or state parameter data. And I did this by iteratively adjusting the values of the coefficients C and N to manually fit the data. Oh, excuse me. So to guide the fitting, I use the following concepts. Oops. So C is directly proportional to QT net. N is indirectly proportional to QT net, and less compressible sands should exhibit higher values of C and lower values of N than more compressible sands. Like I mentioned, the trend lines computed using the equation we showed earlier were developed by iteratively adjusting the values of C and N to fit the data. So let's take a closer look at that first plot. So looking at this first plot, which shows Hoxton sand, we have dimensionless effective stress on the y-axis and dimensionless net cone tip resistance on the x-axis. To draw these families of trend lines, I first bin that data. So for example, for the 20% trend line, I gathered Hoxton sand data with relative densities between 10 and 30%. And after gathering them, I iteratively adjusted the values of C and N until a fit was found. Now I continued this until each bin of relative density or state parameter was completed. And while there are a lot of these interpretations, you can find them if you are so inclined in my papers in the corner. So in their entirety, these interpretations, they represent several hundred manual interpretations, which I've summarized in these following figures. All right, so this plot represents the summary of delta Q, of the delta Q relative density-based overburden normalization. So the plots on top show values of C, while the plots on the bottom show N. So these lines show the bins of relative density. So you can see they're grouped, 0%, 20, 40, 60, and so on. So after going through each soil and iteratively adjusting the coefficients, I plotted them in this chart against compressibility, and I continued this process for all the soils until a trend emerged. So let's zoom in for a second. So as you can see, in this plot of N versus compressibility, the data generally follows the compressibility concept, where soils with similar compressibilities have similar values of N. Now, there are a whole bunch of these summary plots, which you can find in the papers if you are so inclined. So what this leaves us is these correlations to forecast cone tip resistance. To use them, all you got to do is compute your coefficients, and after that, it's all plug and chug. So let me see. Oh, we actually are hitting the time. Okay, so I tell you what, let us just jump forward to how the predictions went. One-to-one plot of just some selected soils Most of them fall, this plus and minus 30% is something out of literature, and most of the predictions fall within that range. And close up, so this shows Hoxton Santacino sand and Toyura sand using the relative density correlations. Again, pretty good, especially when we consider that this represents a significant range of compressibilities and sandy soils. Same thing on the bottom here with state parameter. Pretty good, pretty good. Um, Finally, let's just jump into this. We are going to move forward. It's funny because I had this clocked in at almost exactly 50 minutes, but here we are. So um, this is kind of the result of it all and comparing it to other overburden normalizations. What I want to communicate here is simply that the delta Q overburden normalization falls within the range of of other overburden normalizations in the literature, but tends to be a little bit easier, well, not a little bit, a lot easier to compute. All right, so we're just zooming in there. And this is a comparison in a different, we're visualizing it different. But again, it falls within the range of those other systems while being a little bit simpler to compute. So with that, that is everything there. I'm going to skip over the recap and pass it over for any questions, whether it's related. I'm going to put it out there. I feel like I would like to answer questions related to anything, whether it's, just whatever it is, PhD related stuff, geotechnical related stuff, Army Corps of Engineers related stuff. I want to open the floor up to all that. So I'm going to go on mute and back to you.
All right. Thank you so much. The presentation is very well done, and I felt it was very nice. It felt very understandable, even though I haven't had a geotech class in a little while. So, yeah, I appreciate it. And yeah, the floor is open for questions. Feel free to use the little raise your hand react icon, or you can just chime in on Zoom, whatever you prefer.
Everybody is very quiet.
Well, I don't want to say go, all right, go for questions and then have me be the first one, but I will this time. Uh, so I'm curious about on slide 38, where you're talking about binning the different, how you chose to do the binning. And you said you like had it cut off at like 80, or below 80, the bins were like in steps of two. I believe it's 38. Or yeah, where you talking about the binning of the slides or of the data. Oh, there we go. Thank you. 36. Why did you pick 80? Because I know you said below 80 was like highly variable, but like why 80 and not 100 or 150 or whatnot?
Yeah, that's a fantastic question. It's funny because I feel like practical questions like that actually, I feel like you need a lot of insight to make some of those practical things because I feel like a lot of engineering is based on those practical observations. Um, so when you get below a capital QT of 80, you tend to get into looser and looser soil beds. So to recreate those loose soil beds in a calibration chamber is very difficult. So if I were to use larger bins, there would be a significant amount of scatter. So it took a lot of kind of messing around with the data to see like, oh, actually over 80, there is a little less scatter than under 80. So as soon as I got to those denser soil beds, essentially, um, to kind of ease some of the computation, I decided to use those larger bins.
Hmm. Okay, yeah, that makes sense. Yeah, I was curious about what kind of judgment call it was, but yeah, what you said makes sense. So, yeah, if anybody else has questions, please feel free.
I can go next just to give somebody else more time to think about their questions. But thank you, very informative, just presentation. I'm sure, for especially for our, just students in structural engineering, a lot of like, just interest and maybe new, just information. So It's an interesting concept because you're mainly suggesting to identify just proxies for the properties of the soil in your case, in terms of mechanical properties, starting from, just simple, just tests and on maybe one, just characteristic to kind of extend that to, just other types of properties. And so, of course, my mind goes to more like, structures. And so I was thinking, what's your just view on extending this approach to, for example, concrete? So thinking about, this defining these proxies for now wet materials, not necessarily sand, which I'm assuming was dry, right, for all cases that you presented. So what's your kind of, what are your thoughts on that, the possibility? That would be very, just fascinating for us.
I suspect you might be referring to maybe 3D printing in a sense. Is this
Yes.
so?
To make that characterization simple, exactly. Yeah.
Yeah. I actually think it will work. It will take a little bit of tinkering around with because to get an equivalent property like compressibility
Mhm.
for wet concrete might be a little bit different. But I suspect the framework, I think it would work, especially because in its wet state, I mean that's pretty much like soil, you know. So it would work. It would take some tweaking and a little bit of figuring, but I think the framework is there.
Okay. And as far as literature is mainly focused on you were presenting a lot of works from the literature that's mainly on sand. That's something you just focused on, but in reality, there is just more just that is being addressed in the literature. I was just curious.
Mhm. There's a little bit more out there. So there's some calibration chamber testing on fine grained soils, clays and silts. But I certainly just chose to focus on sands because it was a pretty heavy lift just for the one, the coarse grained soils. But there's certainly more literature out there on calibration chamber testing in other soil types.
Right. Thank you.
And I see we
Go
have
ahead,
a
Greg. Oh, yeah. Go ahead, Greg.
Hey, thank you. Appreciate it. I was curious, since you're part of the Army Corps, was there something in particular that drove the studies? Was there some kind of mission critical or application that they were interested in that sort of drove the funding and the research related to the Army?
So for this one, I'm part of. So we actually have a huge shake table over here, and I've actually been out to the facilities out there in at UNR and senior shake tables out there. But this has applicability um, to scale modeling. So for geotechnical engineering, if you're doing physical modeling, you need to put the geotechnical structure into a centrifuge, of course, because there's these incompatibilities in the state of stress. What we wanted to do on the shake table at Cerro is do physical modeling at normal gravity. So this has applications to that.
I know we're at time, but I do have one more question about like your work and just working for the Army Corps. I know some people got to go at one. If you do, by all means. But I'm curious about so like you're working in the research lab. How does it work? How does projects and applications work in terms of like, do you say, hey, here's an idea, give me the money for it more, or like what you just said of like, oh, there's other backgrounds and somebody needs to figure it out. Like, which one of those is more common in the Army Corps?
It's actually an interesting mix of both because there's a bit of it's almost like pseudo academia, I'd say. So we do have our annual calls for proposal that are focused on certain research topics, but also, and this is kind of a quirk of the government where a lot of our money is it's budgeted congressionally. So um, this type of congressional money has expiration dates. So so a lot of our projects that we do, sometimes people will do a project, maybe something didn't go the way they thought it would, and they now have a lot of money that they have to use up by the end of, or they have to what's the word? I forgot. We have a technical word for it, but they essentially have to account for it before the end of the fiscal year. So they have to say, I'm going to spend it this way. So sometimes there's this fallout money, and just through networking, through maybe people are familiar with your work and it's complementary to their own work. They'll say, hey, Joe, can you do this thing? Can you do this type of research for me? So it's a weird mix of, the calls for proposal and then just going out there and networking and kind of beating the bushes to find the money that exists.
It's fascinating. Yeah, I didn't think about the government funding side of it.
Yeah, and I will say, if you can convince somebody that it's not as easy as I'm saying, but it certainly is possible. If you could pretty much do anything if you can convince somebody that it's related to their mission. And with the military the military has some really complex engineering problems. And the way we split it up in the Army Corps, we have military engineering, we have civil works. Every military engineering project is a civil works project in disguise. So there's really a lot of room for innovation. So you can do some really crazy stuff if you just understand the military application. So it's kind of neat like that, though. Yeah.
That's fascinating. That's an interesting relation between those fields. But so it's a little bit after 1. I don't want to keep anybody too long, but thank you again, Dr. Gomez. This was very interesting, and thank you everybody for coming.